Yeah, so basically this slide is just going through all this analysis we did. It said we want to make all that logic path gate sizes to have the same delay. So we make WA here, WP, WB, that's this one, 2WP, and C and D, 2WP, which we did the analysis, and then WA down here, we made it 2WN, C and D, we made 4WN, and B, we made 2WN. So this is just showing the analysis that I did to give all the paths have the same effective delay. Any questions about that? Sort of a general formula. Looking at this circuit on the left, really what you're trying to find is to find the worst case delay of this gate over on the left is take each individual path and find which has the minimum W effective. So WP minimum in this case would either be WA for this path, right? For the C and B path, it would be the full formula of WC times WA over WC plus WB, sorry. And for the B path, it's WD times WB, WD plus WB. So really the worst case delay is the minimum W effective of those three paths. And likewise for the NMOS, it's the minimum W effective of the two paths, which are, in this case, it's through two transistors, WA times WB over WA plus WB. In this case, it's three transistors, which is, this is the long expression if you expand it out. Does anybody know a better way than doing it this way? What's the other way to do this? You guys remember, did you guys learn about conductances? If I, nobody, maybe silence, total silence. Let's go over here. No, we need a new one. If I give you three resistors in parallel, I don't know, R1 equals 10 ohms, R2 equals 20 ohms, and R3 equals 30 ohms, right? And so you know 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. You could write that big expression for that, and it would look very similar to what we just had here. You could expand that out to this big expression and solve for that. That's kind of painful, especially if you get more than three. Three is bad enough, but if I give you 4 or 5, you're like, oh God, this is break my brain. Oh, which brings me to another of my rules. It doesn't. I'll tell you that other rule later. So we don't do it that way. What do we do? Anybody give me a hint? I don't do this. We don't do this. Nobody knows. We convert these to conductances, right? What's a conductance? We call it like a G, right? G equals 1 over R, right? Is the conductance of that resistance. And so we say, oh, the G total is just equal to G1 plus G2 plus G3. And then at the end, we say R total equals 1 over G total, right? So now this just becomes 0.1. So this became 0.1. It's 1 over 10 plus 0.2 plus 0.3. I add those up. That equals what is that? 6. And then our total is just 1 over 0.6. I didn't have to do all this crazy math, right? Anyway, that's what we do for W's. If you get a bunch of W's in parallel, take their reciprocals and add them up, and then just take the reciprocal of the final number.
In series, you mean?
If they're in series, if the transistors are in series. If they're in parallel, you just add them. But if they're in series, take their 1 over W values, the equivalent of their conductance for resistors. Okay, so that's the case when we have there. And as we talked about last case, these are worst case delays we're trying to figure out from these equations right here and here. If we want the best case delay, we assume all the paths are on. So the best case delay for the P's would be all P channel transistors on, and the best case for the N's would be all N channel transistors on. So we are kind of interested in this best case delay. We'll see later on why. And we're interested in these worst case delays. And usually we're interested in the worst of the worst. Like I get the WP for the N's, P's, W effective for the P's, or the W effective for the N's. And then depending on their mobilities and their effective WP, I get the worst case of both the N's and P's. And that's the one I'm really interested in the most because it's the worst of the worst. Any questions? We're going to do one slide, then we're going to have some bonus questions. So we've been using, we learned about, let's go back here. We learned this logic, right, which we called resistor transistor logic, right?